Alright, welcome back everybody. In this video we are going to be talking about information from section 10 of Unit 2 of AP Calculus, finding the derivatives of tangent, cotangent, secant, and or cosecant functions. Okay, and we're going to start off by developing the rules for the derivatives of these four functions. Remember, a few sections back we learned the rules for the derivatives of sine and cosine. The derivative of sine is cosine of x, and the derivative of cosine is the opposite of the sine of x. And we're going to use these and the quotient rule, which we just found in the last section, in order to develop all the other derivative rules for the other trig functions. Okay, so unlike the way we've been developing most of our derivative rules, we will not be using the limit definition of the derivative in order to come up with these rules. We will instead be using these two derivatives here, and the fact that we can break these other trig functions down into pieces with sines and cosines, and the quotient rule. Alright, so let's go ahead. We'll start with the derivative of tangent of x. Now tangent of x is equal to sine of x over cosine of x, and so the derivative of tangent is equal to the derivative of the sine over the cosine. And so we can proceed from here by using the quotient rule. And so this derivative is going to be equal to low times the derivative of high. The derivative of sine of x is cosine of x, minus high times the derivative of low. The derivative of cosine of x is the opposite of the sine of x. Square the bottom, and away we go. And let's see where we go from here. Cosine of x times cosine of x gives me cosine squared of x. Minus sine of x times the opposite of sine of x gives me plus sine squared of x. And this is one of those things that I feel like just everybody who's taken enough math to get to calculus knows that cosine squared of x plus sine squared of x is equal to 1. So we're going to go ahead and use that Pythagorean replacement here. And this is 1 over cosine squared of x. And 1 over cosine squared of x is equal to the secant squared of x. And so there's my rule for the derivative of the tangent. The derivative of tangent is equal to secant squared of x. Alright, let's go ahead and we'll do the same for cotangent. We'll split it up. Cotangent is equal to cosine over sine. So cotangent of x is equal to cosine of x over sine of x. And now we'll go ahead and we'll use the quotient rule. Low times the derivative of high. The derivative of cosine is the opposite of sine, minus high times the derivative of low. The derivative of sine of x is cosine of x. Square the bottom, and away we go. And we simplify from here, and that gives us negative sine squared of x minus cosine squared of x all over sine squared of x. And if we factor a negative 1 out here in the numerator, we're kind of in the same position that we were when we were finding the derivative of the tangent, where we have that sine squared of x plus cosine squared of x that everybody tends to recognize as 1. And so this simplifies to negative 1 over sine squared of x. And 1 over sine of x is the cosecant, and so this is equal to negative cosecant squared of x. Alright, 2 down, 2 to go. Up next, the derivative of the secant of x. And if you remember correctly from previous courses, secant of x is equal to 1 over cosine of x. And so this is equal to the derivative of 1 over cosine of x. And we can go ahead and find this derivative again using the quotient rule. Does it make sense to everyone why we waited to develop all these rules until after we had learned the quotient rule? Because we're using the quotient rule in the development of all of them. And it's a whole lot easier this way than it would be trying to develop them using limits of difference quotients. So anyway, low times the derivative of high. The derivative of 1 is 0, minus high times the derivative of low. The derivative of cosine is the opposite of the sine. Square the bottom, and away we go. And simplifying this is sine of x over cosine squared of x. And instead of leaving it that way, notice that we've written all the rules so far in terms of, not sines and cosines, but the most simplified, easiest to write trig functions that we can. We're going to do the same thing here, and in order to do that, I'm going to split this fraction up. Sine of x over cosine squared of x is equivalent to 1 over cosine of x times sine over cosine of x, and 1 over cosine is the secant of x, and sine over cosine is the tangent of x. And there you go. The derivative of the secant of x is secant of x tangent of x. All right, last one, derivative of cosecant of x. Cosecant is 1 over sine of x. And so again, using the quotient rule, I've got low times the derivative of high minus high times the derivative of low. Derivative of sine of x is cosine of x. Square the bottom, and away I go. And I've got negative cosine of x over sine squared of x, and I'm going to do the exact same thing that I did last time. I'm going to say this is negative 1 over sine of x times cosine of x over sine of x, and negative, I'll pull out in front, 1 over sine of x is just the cosecant of x, and cosine of x over sine of x is the cotangent of x. And so the derivative of cosecant is negative cosecant of x cotangent of x. And there we go. All of our derivative rules. If you turn to the next page, you'll see them all listed here. I have these rules kind of organized so that you can see that there are some similarities and some things that will help you to easily remember them. If you notice, all of the non-cofunctions, so the sine of x, the tangent of x, the secant of x, for all of those, when you take the derivative of them, the result does not contain a negative. But for all of the cofunctions, ooh, I found a typo. My goodness. For all of the cofunctions, there is a negative in those. Man, that typo really threw me for a loop there. All right, so I got to fix that. But then you can see, some other relationships, they're tied together, horizontally here as well. The derivative of sine and cosine are tied together, where the derivatives of each other contain each other. The derivatives of tangent and secant are tied together. The derivatives of cotangent and cosecant are tied together. If you take the derivative of the tangent, the derivative of its cofunction is the opposite of the cofunction of the derivative of tangent. So there are all sorts of patterns here that you can see in this, and so hopefully that will help you to remember some of these derivative rules. All right, let's go ahead and we'll do example 1 here. Find the equations for the tangent and normal lines to the curve y equals tangent of x at x equals pi over 6. So it's been a while since we've done a tangent and normal line. We used to use the limit of the difference quotient to find the derivative, but now we have all these derivative rules to help us out. So this is going to be a whole lot easier for us. So we need 2 things to write tangent and normal lines. We need the point that the line goes through and the slope of the line. So the first thing I'm going to do in this problem is I'm going to find the y value when x is pi over 6. And so I need the tangent of pi over 6. And the tangent of pi over 6 is square root of 3 over 3. So these lines are going to go through the point pi over 6, comma, square root of 3 over 3. Okay, now I need the slope. So in order to find the slope, I want the value of the derivative at pi over 6. So first I'm going to find dy dx here. Let's see, dy dx for tangent of x is secant squared of x. And so dy dx at x equals pi over 6 is equal to secant squared of pi over 6, which is equal to 2 over the square root of 3, quantity squared, which is 4/3. So this is going to be the slope of the tangent line. And now I can go ahead and write those equations. The tangent line is going to be y minus the y coordinate of the point is equal to the slope times the quantity x minus the x coordinate of the point. And the normal line is perpendicular to that one, so the slope of that line is going to be the opposite reciprocal, and so the equation for that is going to be opposite reciprocal slope and x minus pi over 6. All right, so just to kind of verify this real quick, let's go ahead and we'll take a look at the graph of this function and the graphs of the tangent lines and normal lines. Okay, so we're talking about the graph of y equals tangent of x. There we go. And we're finding the tangent and normal lines at pi over 6, which pi over 6 is a little bit more than 0.5, so somewhere right around in here is where we're looking at these tangent and normal lines. So if I go ahead and type in the tangent line, let's see, y minus square root of 3 over 3 is equal to 4/3 times the quantity x minus, times the quantity x minus pi over 6. Pi over 6. Okay, there you see the tangent line to the curve there, and the normal line is same thing, y minus square root of 3 over 3 is equal to, only it has opposite reciprocal slope. And so you see that line goes through the same point, except it's perpendicular. And you see the function, the tangent line, and the normal line at pi over 6. Okay, so there's what that looks like. All right, we're going to call it quits for this video, and we'll come back next time with hopefully the rest of the examples from this lesson on the derivatives of the other 6 trig functions. All right, everybody, have a great rest of your day, and I will see you next time. Thanks for stopping by.